Thank you, Matthew. Thank you for the opportunity to present to you EOS, a software for flavor physics phenomenology, which I'm presenting on behalf of all of the EOS authors. Thanks also for accommodating me on short notice to move the talk around a little bit. I appreciate that very much. So let me move the faces out of the way. So yeah, EOS is a software for a variety of applications in flavor physics. It's written in C++, so ordinary it wouldn't fit in here, but it provides an interface to Python, and actually the Python interface is the recommended interface to use EOS. And we highly recommend to carry out all analyses with EOS within a Jupyter notebook, just like this presentation is one. And if you're interested, you can find the list of all the contributors behind this link here once I upload it to the Indico. Okay, so why can't I move? I can move on. Very good. So EOS was written with 3 use cases in mind. First, to produce publication quality theory predictions for flavor observables. Second, to infer theory parameters from a set of likelihoods. It's actually an extendable database of likelihoods that comes with EOS, and which you can extend on your computer in addition to what is provided via PyPy. And third, to produce high-quality Monte Carlo samples of flavor processes, for example, to conduct sensitivity studies. So what follows is a very condensed presentation of these 3 use cases, and the complete tutorials are available online behind this link here on the EOS GitHub page. Very good. Some preliminaries. Of course, if you want to follow this, you need to install EOS. So it's as easy as running pip3 install EOS app, because EOS had already been taken. Not too surprising. If you want to try it, you will need Python version 3.7 or higher, which should not be hardship. And to load EOS into your notebook or any other Python interpreter, simply import EOS. And let me do that right now. That worked very well. And for later use, we will also need NumPy. So I seem to have forgotten to clear all the outputs, but let me do that nonetheless. Very good. So with the preliminaries out of the way, let's get into the first use case, the theory predictions and uncertainty estimates. So EOS was built to provide accurate theory predictions of a large number of flavor physics observables. And this, of course, includes determinations of the uncertainties, which we do in a Bayesian framework. So first, let's start with what these observables are. And to get an idea, you should inspect them. EOS features more than 1,000 pseudo observables that can be readily predicted. And when we're writing pseudo observables, we mean basically everything that EOS predicts is considered an observable, even though it's not a physical observable. So pseudo observable that can be predicted are, for example, certain hadronic matrix elements, so-called form factors, which are functions of kinematic variables, which have a common interpretation, but that are really not physical observables. Nevertheless, they can be obtained, for example, from lattice QCD, from continuum QCD methods, and they sometimes need to be averaged. They need to be checked against each other. So we count them as a pseudo observable. The total list of observables is available online behind this link, or interactively within a Jupyter notebook. So let's actually try that out. What I'm doing here is I'm constructing the observables class, and I'm filtering. I'm filtering for a D-meson in the process, and for observables that include BR for branching ratio. So let me do that. This is the output. Not very informative right now. It says the observables in a number of semi-leptonic B-hadron decays. But because this list is so long, what we have done is we have by default collapsed everything. And if you click on it, you can see a little bit more. Now the rest is almost out of view, but that doesn't really matter because we can focus on these 2, which will be used in the remainder of this presentation. So B2DL new is the process that I want to focus on. BR is the integrated branching ratio. You see the nice mathematical symbol that's usually used for it. You see what kinematic variables it requires. And for the so-called, well, let's call them power users, you see all of the options that can affect such an observable. These options are consumed by the observable upon construction and cannot be changed thereafter. And they include, for example, the choice of model, which is defaulting to the standard model SM, but can vary to, or can be changed to, for example, CKM, which is kind of the standard model, but all CKM matrix elements will be promoted to independent parameters with 2 real degrees of freedom. So you can fit absolute value and phase of each CKM matrix element. Or WET, which stands for weak effective theory. So if you're hunting for physics beyond the standard model in these processes, this gives you access in a model independent way to the effective field theory couplings that can modify your processes beyond the standard model. Similarly, we can open up the form factors. So hadronic form factors describe these processes since they are genuinely non-perturbative quantities. There are varieties of parameterizations that can be used. Basically, all of these names that you find here are available online in the documentation in a list of references. You can click on them and see what these form factor models are and what parameters they have. Right, so as I said, these two observables, the latter one, the differential one in the variable q square, which is the invariant mass of the lepton neutrino pair, will come a little bit later. Let's focus mostly on the branching ratios and collapse this. Very well. So how do you construct and evaluate an observable? EOS uses these observable objects as the basic building blocks for all types of analyses. They can be interactively constructed in a notebook as follows. So to make an observable, you run observable make. You need the name. You need a set of parameters. If you make several observables, you can share parameters between them. This is how we do the fits. By shared parameters object. You need to supply a number of kinematic variables. They're encapsulated in a kinematics object. And you need to provide an options object, which can be empty, but in this case is pre-populated with an option that sets the lepton flavor to a mu lepton. So if you do this, very well, we get the following output or display for this object called OBS. It's a B2DL branching ratio observable. That's no surprise. The kinematic variables as we set them and the current value of the observable. You can evaluate it using the evaluate method. You can inspect it further, but I don't have the time to do that right now. All of the methods that affect an observable are listed in the online documentation. So as I said, we need this set of parameters, kinematic variables, and options. But for more complicated, more advanced applications, they will likely be provided in a more structured way. Then, now that you have an observable, typically what you want to do is you want to visualize it. And EOS provides some plotting framework for that based on matplotlib that can illustrate any number of observables that you're interested in. And it accepts a dictionary like this. So what you see here is that on the x-axis, we put the q-square variable, this kinematic variable, in a certain range. On the y-axis, we put the differential branching ratio. We put the legend somewhere convenient. And we plot two plot items, contents items of the type observable, here. And the observable that we're plotting is this differential branching ratio for muons and for tauons. And this is what comes out of the whole exercise. Of course, this is a typo that should have been figure. So if you run this and you want to modify your matplot figure for some reason afterwards, you can access the matplotlib objects which are returned like this. Very good. So we have illustrated two observables. What else can we do? Well, we can estimate the theory uncertainties. Just having these narrow curves here is not, well, it's not quite all that we want from it. We want to produce some bands that show us the theory uncertainties. Again, we default to Bayesian statistics to determine the theory uncertainties. And to do that, we define our posterior using the EOS analysis class. There you specify your set of priors, your likelihood, and therefore overall your posterior. And it's quite short. What you need to do to create any EOS analysis object, you need mandatorily the priors, which is a list of prior specifications. They contain their parameter name, min and max range, and the type, in this case uniform. In the documentation, you can see more than uniform priors. We have Gaussian priors. We have specific theory priors that use a Gaussian distribution for logarithms of your renormalization scale, and so on. But you also need the likelihood. So in this case, it's a list of constraint names. These names can be found online in the list of constraints, or you can look them up with eos.constraints in a notebook. These are two constraints by the HPQCD and Fermilab Milk collaborations for these B2D semi-leptonic form factors. Okay, so let's create that object. Very well. What we can do now with this object is we can sample from its posterior. The parameter samples that we obtain will require some Monte Carlo sampling. The simplest approach that EOS provides involves Markov chain Monte Carlo sampling, so Metropolis Hastings, but more sophisticated algorithms like population Monte Carlo and nested sampling are available, i.e. the interface to external software that implement these algorithms is available. So we're using the PyPMC package for MCMC and population Monte Carlo, and we're using Dynasty for nested sampling. Posterior predictive samples for any number of observables can be obtained in parallel to the posterior samples. If you're defaulting to the Markov chain Monte Carlo, and it looks like this. So we're producing some Q-square values for this decay B to D tau nu in the differential branching ratio. We make a number of observables in this very Pythonic form. We share the same analysis parameters for all of these observables, but they have individual kinematics. And the tau is selected for the lepton flavor, the BSZ 2015 parameterization for the form factors. And then we go about it. We sample from our posterior and tell it, oh, please also do some posterior predictive distributions for the observables, especially these observables. We obtain a total of 5,000 samples, and then we're done. Quite fast. Very nice. Using these samples, we can now illustrate the posterior prediction and therefore the theory uncertainty. And it looks like this. So instead, the plot setup with the X, Y axis and the legend is the same as before. However, the contents has changed. There's a single content item now, which is not of type observable anymore, but of type uncertainty. The other items for this are also documented online in the on the web page. The change that we have now is that we provide some data in form of the samples of the posterior predictive samples and the corresponding Q-square values. And we can plot it and get this nice band corresponding to the 68% uncertainty envelope of our prediction. Very good. Let me continue with the second use case, parameter inference. So as I said before, EOS can be used to infer parameters from either experimental or theoretical likelihood. It really doesn't care. It treats them all the same. And again, it defaults to using a Bayesian framework. So what we do is extending the analysis that you saw before by adding two experimental likelihoods for measurements in several Q-square bins of the branching ratio for B0 to D plus E minus nu decays or mu minus nu decays. They're coming both from this publication by the Bell collaboration, and as for all these names, you can look them up in the list of references where you find a hyperlink to the preprint and to the publication. In addition to the two experimental likelihoods, we also add the CK matrix element VCB, or rather its magnitude, to our list of priors. The full list of constraints, I said that before, but I hadn't written it down. I do it here. The full list can be inspected interactively using EOS.constraints or via this hyperlink. And let's set up the posterior. So as I said, we are now at one prior and two pieces of experimental data to the likelihood. So this is what our construction of the analysis looks like. So this first line here is new. It sets some global options that affect all of the observables that are used within the analysis. So all of the observables that are created as part of the likelihood will be affected by these options rather than providing them individually. So all observables use the same model the same parameterization for the form factors and the same model, this CKM model. So all observables are in principle sensitive to the magnitude of VCB and all of the form factor parameters as before. And these two pieces of experimental data have been added. In addition, we set the VCB value to some kind of sensible initial value before we proceed. Very well. The next step is to optimize the posterior and check if we obtain a good fit. So we do this by defining or obtaining our best fit point using analysis.optimize. We display it and we display a goodness of fit summary. And that's also quite quick. We get this value of 41.9 times 10 to the minus 3. The form factor parameters are very close to their prior values. For the goodness of fit summary, you find for each constraint the chi-square value, if applicable. EOS supports multivariate Gaussian likelihoods, but it also supports likelihoods that are outside of the family of Gaussian distributions. For those, of course, we do not list any chi-square value, and we cannot include these in the total goodness of fit summary. So for each constraint, chi-square, the degrees of freedom, and the p-value, assuming that there were no parameters. So all of these would give a reasonable fit. And taken together, we find this total chi-square for 26 degrees of freedom, corresponding to these numbers of observation minus these now 6 parameters, giving a p-value of 60%, which is a good fit. We're very happy with that. Very good. The next step is to determine the uncertainties on our fit parameters. To that end, we draw samples of the posterior PDF. And again, we're using Markov chain Monte Carlo as the least sophisticated method available, because this is a very easy analysis with only 6 parameters. What we're doing here is we're initializing our random number generator. This is optional. I wanted to just showcase it here to make your analysis reproducible. We're obtaining the parameter samples from EOS analysis sample. We take 5,000 samples with some configuration for adaptive pre-runs, which filter out only take every 5th step along the way, and a total of 2,000 steps per pre-run. We're also starting our Markov chain at the best fit point that we obtained earlier. You can see that the Markov chains adapt quite quickly, and for the main run, we get an acceptance rate of 25%, which makes us quite happy, and we can proceed to visualize what these results look like. And due to the time constraints here, I will only do that for the one-dimensional marginalized posterior for the VCB parameter. So to do that, we're using the plotting framework again. We put VCB magnitude on the x-axis, put the legend at a convenient position, and show both the samples that we obtained in form of a histogram and a kernel density estimate of the samples. We do that right now, and you can see our histogram and our KDE agree very well with each other, as they should be. We get a value of 42 times 10 to the minus 3 plus minus roughly 1 times 10 to the minus 3, and we can actually investigate that a little bit further by taking the mean and the variance of our samples and plot them, and you see, yeah, 42, that fits quite well, and I was overestimating the standard deviation a little bit. Excellent. So let's come to the last major use case, Monte Carlo simulation of pseudo events. EOS can provide these Monte Carlo samples of a variety of flavor processes. And these have been previously used to conduct sensitivity studies in the context of experimental analyses. So to see the full list of signal PDFs from which we can sample, this EOS.signal PDFs inspects them interactively within a Jupyter notebook. So let's do that. Again, I'm applying a filter because the total list would run out of the boundaries of my presentation or screen real estate. So there are 2 of the signal PDFs. We're going to concentrate on the first one, which is the one differential distribution. It's differential only in Q squared, this dilepton invariant mass, rather than the full differential distribution, which is also sensitive to the cosine of the helicity angle between the lepton and the neutrino pair. Very well. So using this signal PDF as an example, we're actually splitting that into 2 examples. We want to simulate final states with a muon and with a tauon. So we set up some kinematics for the muon case. We produce our signal PDF from this name, a set of parameters, our kinematics, and the default options, and sample from it using sample MCMC. We obtained a total of 20,000 samples from this process after some adaptation to our Markov chains. We do so with a pre-provided random number generator. So again, this will be a reproducible step. And we repeat it for the tau lepton, for which we need to adjust the kinematic range to the minimum, the left end of the kinematic range to the tau mass. Again, reproducible, very quickly obtain these tau samples. And in the next step, we visualize them, and we're comparing them with a true signal PDF, which is available. So in our plot, X now shows Q square. On the Y-axis is the PDF. Legend is conveniently located, and we have 4 plot items, 2 histograms corresponding to our muon and tauon samples, and 2 plots of the analytic PDFs. Again, for the muon and the tauon sample of the type signal PDF, and selecting the signal PDF simply by the name. We can provide options, as I said previously, by simply appending them to the name of any signal PDF or observable. And doing this produces this nice picture below, where you can see that our Monte Carlo samples very neatly reproduce the shape of our analytic expression. Excellent. So what have I not shown to you today? An in-depth presentation of EOS would have taken more time than allocated for this introduction. There were 2 major elements that were not shown. One, to provide that EOS provides code for a number of what we call tasks that are common to all Bayesian analyses. This is existing and working code. It has been successfully used for a few projects already. However, the documentation is not complete, and we are working on that. The tasks have a very well-defined way to store and share their data. The analysis description is common to all tasks and is done in terms of a single YAML file. So if you're interested in that, we have some preliminary documentation for that, and I can share that with you. Tasks can be run both within a notebook and on the command line. And the latter is quite important if you want to do batch jobs in a cluster environment. Not all of the analysis that you do with EOS, as I've shown you today, not all of these analyses are this quick. Some of them take hours, days, and if you do that and want to do that in a cluster environment, the command line tools which use the tasks framework are what you're looking for. The second major item is that we are in the process of making our analyses reproducible. So beyond recording the priors, the options, the likelihoods of our analysis, we also want to record the settings. That is the number of pre-runs, the number of samples per pre-run, the overall number of samples returned for the whole analysis, and so on. And we're making progress in this regard, but this is not quite complete. And with this, let me come to my conclusion. This was a really short but quite dense summary of the EOS use cases. More detailed tutorials are available online in form of interactive Jupyter notebooks. The documentation, the link you see here, includes non-interactive HTML versions of the tutorials as well, which are more extensive than this. We are always happy to extend EOS by adding new features, observables, PDFs, and so on. If you're interested in that, let us know. The best way to do that is via our Flavor Physics Discord server, where we also provide support for EOS. If you do join via the link behind this, the invite link here, feel free to drop by in the channels EOS or EOS Dev. And we are very welcoming to all new users or prospective contributors. So thank you very much for your attention. And if there's time, I'm happy to answer any questions you might have.
Yeah, excellent talk. It's always really nice to try and to see these sorts of tools, and it's also nice to see tools that are using Bayesian techniques. So I think we have time for at least one question, maybe two if we're fast. So let's go to Slido. There are some comments that I think are generally useful, but I'm going to go to Nick Smith's question first. And he asks, is the full dimension 6 Warsaw basis of SMEFT operators available? And have you tried any global fits? And if so, how well did they scale?
Okay, so this assumes that we're using SMEFT at all, which we're not using. For flavor physics, SMEFT is not the best choice of effective field theory. Instead, the weak effective theory is the theory of choice. And this effective theory lives at a low scale of, let's say, a few GeV. Of course, it can be matched onto SMEFT. There's a paper which does this matching at the one loop level by Wouter Dekens and Peter Stoffer. There are other Python utilities that you can use to interface with EOS to obtain flavor physics constraints on the SMEFT coefficients. And no, we've not tried a global fit yet, because the total number of SMEFT operators is, I think, in a flavor anarchic setup, it's slightly less than 2,500, and you simply don't have enough complementary flavor constraints to achieve that.
Yeah. And Nick's, oh, sorry, Nick's connected. I'll let him talk. Sorry.
All right, a small follow-up. So I guess this means that you can't do any running of the scale up to sort of like energy scales that we're probing SMEFT models and CMS analysis.
No, this is specifically for low energy flavor physics. So BDKs is kind of the highest scale that we're accessing. If you want to use this in connection with a SMEFT analysis, I recommend to use EOS in connection with Wilson. It's a Python package that can match and run. So it can match from SMEFT to wet and run your parameters both in the SMEFT and from your matching scale in the wet down to the B physics scale or charm physics scale or strange physics scale, whatever you prefer.
Okay, cool. So there are packages out there to do the running.
Yes.
Awesome.
Yeah. Okay, so thanks again for that talk, Danny. Really, really nice.